Hello, everyone. Welcome to our presentation today. We are going to be going over containment and ground modification. This is presented to you by myself, Jonathan, and my teammates Sabrina and Daniel. So, a brief introduction to what this presentation is going to look like. We will first begin by describing the physical mechanisms that make containment and ground modification a successful treatment method. Next, we are going to introduce some of the influencing factors that both hinder and help the method. We will then move to field implementation, where we describe techniques and equipment setup for containment and ground modification. And from there, some case studies will be presented that show this method in action, and we will dive deeper into what makes this method useful, where it succeeds, and where it may struggle. We will then wrap up the presentation by viewing the cost and availability for these methods. Looking at the containment methods we're going to discuss briefly here, starting with hydraulic containment, these typically come in the form of pump and treat. We'll also get into some physical barriers like slurry walls and sheet piles within the ground. And then we'll look at some surface caps that help prevent percolation. So hydraulic containment is typically done by utilizing pumps in a pump and treat operation. For this presentation, we will focus on the pumping process of pump and treat, as the treatment process is kind of a whole different thing on its own. So the driving factor here in this method is the creation of cones of depression. These cones of depression change the groundwater flow towards the direction of the well. This creates a capture zone, which allows for efficient removal of that contaminant that is within the water table. It's also used to control plume migration. It prevents that contaminant from spreading any further downstream. And an important aspect of this treatment method is ensuring that these cones of depression overlap each other. If the cones don't overlap each other, you can get gaps in hydraulic control and portions of that plume that can bypass the capture, and you get an overall loss of containment. So when constructing an multiple extraction well project, you want to ensure that these cones of depression overlap each other to ensure the maximum efficiency of removal of that contaminant. So next, we'll get into some of the physical barriers, starting with slurry walls. These typically consist of soil bentonite or cement bentonite, two different types of clays. They will have a much lower hydraulic conductivity and permeability than the surrounding soils. This helps to reduce overall groundwater flow through the area. Uh, they physically block uh, advective transport pathways. Therefore, the groundwater can't pass through the wall very easily, and the flow will be directed either around the wall or it can be slowed down, as seen in these two images here. The top one is showing a scenario where there's a slurry wall placed around some waste material, and it's containing that waste material where we want it to be. And we can also install a slurry wall in order to slow the transport of this uh, waste material, whatever it may be, as seen in that bottom image. What these walls also do is they can reduce pore space as they're used. As the water contacts these slurry walls, the clay swells within them, which is kind of a self-healing mechanism. It can fill any voids and cracks, and it helps to maintain the low permeability that these clays have. And then an additional benefit of these walls it can provide an increased structural integrity of the subsurface area. So next we'll get into sheet piles, which are pretty similar to slurry walls, except these are made of steel, and steel itself is essentially impermeable. However, at the joints of these walls, there are imperfections where water can get through. So it essentially acts as a low permeability barrier. This permeability can be tested through dye tests to determine how permeable these barriers are. And these sheet piles that are rated for low permeabilities typically force the flow to reroute to go down to the bottom of the wall. Sheet piles also provide high structural strength, higher strength than compared to slurry walls, being that they are made of steel, and so they provide kind of a slow or no flow or slow flow boundary, and can contain water and contaminants that may be in the water. But typically, these types of walls are used for water containment to prevent flooding or anything like that. The next physical barrier we will talk about is surface caps. Surface caps are designed using layered systems. So there's a low permeability layer, which is typically either clay or geomembrane or both, and this blocks flow going vertically. There's also a drainage layer, which will remove any water that reaches to that point laterally. And there's a vegetative layer at the top, which promotes evapotranspiration, further preventing any water from reaching the contaminants below. So a main driving force here is the reduction in Darcy's flux. So Darcy's flux drives mass transport. If Darcy's flux becomes lower, mass flux becomes lower. So the main goal here is to disconnect contamination from the hydrologic cycle. This will prevent rainfall infiltration and any recharge-driven plume expansion. What surface caps do is they essentially isolate the contaminants from any external water inputs. Now it's time to move on to the ground modification methods that are going to be discussed. These will include soil stabilization, permeable reactive barriers, or PRBs, and in situ oxidation/reduction. First up here, we're going to talk about soil stabilization and solidification. This is a treatment approach where binding agents like cement, lime, or other additives are mixed with the contaminated soil in order to reduce the mobility of the contaminants. Like the other methods discussed today, it's not necessarily to try to destroy the contamination, but it's just to make it much less likely to spread throughout the environment. So the first reason why this method is effective is the encapsulation and entrapment. So when these stabilizing agents are mixed into the soil, the contaminants will become physically locked within the treated soil matrix. This will reduce the ability of outside water to contact them and reducing the ability for these contaminants to migrate. This method also introduces a lower permeability. The treated soil becomes much less permeable, meaning groundwater cannot move through it as easily. This will also lead to a reduced leaching area, and since the contaminants are locked in with this matrix, there is less exposed surface area available for water to contact and dissolve the contaminants out of the soil. And in turn, this is going to cause flow diversion. Because the treated mass is much less permeable than the surrounding soil, the groundwater is going to tend to move around it instead of through it, which further helps to isolate that contaminated zone. Another mechanism here is diffusion control. Even if some of the contaminants do dissolve within this matrix, they will move outward very slowly because they have to pass through such a dense structure. This is going to greatly slow that contamination migration. The last talking point here will be the strength and durability of this new soil. The treated material will become much more resistant to erosion and cracking or any other physical breakdown, which can help this method remain effective over a long period of time. So now we're going to look at some permeable reactive barriers, also known as PRBs. Unlike the past treatment methods we've talked about, this one is actually trying to treat the groundwater. It's not trying to restrict the flow of the water, instead it encourages it, which allows for the water to pass through this reactive barrier and in turn get treated as displayed in this image right here. So the first physical mechanism that is required to make PRB successful is the permeable flow through design. The barrier has to remain permeable enough so that the groundwater will move through it rather than around it. This will allow for the best and most effective treatment of the groundwater that's contaminated. So, in order to get treated, PRBs use sort of reactive contact mechanisms like sorption and adsorption, where contaminants will attach to the surface of the reactive material and they are removed from the flowing groundwater. We can also see precipitation or co-precipitation, where dissolved contaminants are converted into solid phases that are less mobile and they will remain within that barrier. PRBs also can promote redox transformations, where contaminants are chemically changed into a less harmful or less mobile form through oxidation and reduction reactions. The last ground modification method we will discuss is in situ oxidation and reduction. This is an approach where chemical reagents are injected directly into the contaminated soil or groundwater, so treatment will happen in the ground without having to excavate the soil or pump all of the groundwater to the surface. The first physical mechanism that makes this method successful is mass transfer. For treatment to occur, the injected reagent has to move through the subsurface and reach the contaminated zone. But at the same time, that contaminated mass must be accessible, meaning it has to come into contact with the reagent either in the pore water in an aqueous form or along the soil surfaces. The second mechanism is chemical transformation. Once contact occurs, the oxidizing or reducing reagent reacts with the contaminants and changes them into a different chemical form. Ideally, these reaction products are less toxic, less mobile, or easier to manage than the original contaminants. A third important mechanism is precipitation. In some cases, especially for certain metals, the chemical reaction changes the contaminant into a form that is less soluble, causing it to precipitate out of the groundwater and remain in the solid phase. This is going to reduce its overall mobility and it helps to keep it from spreading further down the aquifer.
Okay, so now we're going to talk about some influencing factors. And the first one we're going to talk about is the containment method. In general, this method is useful if your contamination is too large or your aquifer is too deep. These two variables make it really difficult and really expensive to try to do remediation immediately. So if you want to have something to just stop that contaminants before it spreads too much, you can use the containment method as a quick sort of solution to make sure that you are being as mindful as possible. And some influencing factors with that are hazard level and permeability. If it's too hazardous, you again want to stop that spread as soon as possible. So you're going to use some containment methods. And you also, in general, for this method, want your permeability to be low. This allows your methods to stay stuck in the ground, as well as make sure that your spread isn't as big, so it's not going to move around your methods of containment. And now for some more in detail, we're going to go on to the pump and treat for containment. In general, you need water-soluble contaminants for this method to work because this method is fully based around moving water. So you want to make sure that your contaminants are in that water and they don't have a high soil affinity so that they're going to stay with the soil instead. You want it to have that low soil affinity, be soluble, so it will go up with your water and then be treated. It's also really important that you understand the geology of the area really well. So when you're modeling your system for where you want to place your wells, you want to make sure that all your cones of depression are falling into good areas so that you're collecting your whole plume area and that you're not only hitting some spots or you're leaving some other spots out. It's also important to be aware of your local water bodies to make sure that those aren't being pulled into your new groundwater flow that you're creating with these cones of depression. For example, one of the issues that can come up with this is saltwater intrusion. You don't want that to come into your system because it can impact the way you treat it and not provide the clean water that you want, or it can just impact the whole system and your contamination and create new reactions. Another method of containment are slurry walls and capping. And these methods for slurry walls, you need a really low permeability bottom to prevent water from going around your walls. So you want to make sure that they're contained where they're supposed to be and they're going to be stuck in those walls. It also helps create a stable area for your walls to go in and that they will be stuck in the ground. For capping, this one's a little bit different than the other two methods, the pump and treat and the slurry walls, and the fact that it's not as much groundwater remediation, but you want to prevent any groundwater mishaps to go through. So when you're getting your stormwater through contaminated soils, you want to prevent that leaching, that toxic leach. So for capping, you want it to be in a more shallow area because you're going to want to put that synthetic liner all the way on the bottom before you're putting things into it. Okay, so now for some ground modification methods. In general, this method is not reasonable if your soil depth is too deep because this makes it really difficult to reach it, especially for this method. You don't want your soil permeability to be too high or too low. These methods does depend on whether you're looking for the high permeability or low permeability, but if it's too high in either direction, it's typically not going to work. And it's not reasonable if your contaminants are too hazardous, just because when you're doing these kinds of methods, you don't want to continue to leach out your contaminants. You want it to still be compliant with everything. Now for the three specific methods on this for ground modification methods, we first have soil stabilization. So for this one, it was said that you need to have not too deep, but if you did want to increase the depth, so you could try to use this method, you can use site benching or site sloping. This diagram on the bottom with the two pictures shows what sloping and benching looks like. These are just engineering methods and excavation methods that are used to get down deeper without compromising the sides of your walls to make sure it's going to stay safe and it's going to stay structurally sound so that there aren't any breaks or anything. You also want to make sure that there's not too many rocks in the way or debris or other kinds of materials in it. You want it to be all kind of homogeneous because for soil stabilization, you want to have that correct chemical composition throughout the whole thing to make sure that everything is stable where it needs to be. So if there's too many rocks or too many debris, it's not going to be able to work the way it's intended to, and it can cause an issue. You also want it to have stable ground. This is important because when you're putting all of these materials in, it can cause some fracturing if the pressure is too high. And if your ground isn't stable and this isn't accounted for, then it's going to cause those fractures, and those contaminants are going to go out those ways instead of being stuck in the soil like it's supposed to with soil stabilization. So having stable ground is really important, that you make sure you're containing and keeping all those contaminants where they're supposed to be and not through other pathways that are created when you're trying to construct this whole thing. For permeable reactive barriers, you can use fracturing to increase your depth. So in soil stabilization is typically the sloping or benching method, but for this one, you can use fracturing to increase your depth. But along with that, you do want to make sure that when you're fracturing, you are doing it in the place that it's supposed to be in. So you again want to have that stable ground to make sure that when you're fracturing, it's not going further than you want it to be, and that your contaminants are going to go out other places that you don't want it to be in. You want it to be contained right in that area where you're choosing to fracture your material. And for oxidation reduction methods, once again, you can use that fracturing, but this time, instead of increasing depth, you're trying to increase your permeability. This method relies heavily on injecting things into the ground so that you're remediating typically in situ, which means like just within the ground. So you want that high permeability for it to reach all the areas of contamination. This also, having that low permeability, it's not ideal because you're going to decrease your radius of influence or ROI. This means it's just not going to spread as far as you want it to, so you may have to have several injection points, which can be more costly. And if it has low permeability, you also have a higher chance of creating high pressures, which can cause unwanted fracturing, again, going into that contaminants are going to go where they're not supposed to with new fractures. So in general, you really don't want low permeability for this method. And you also want to make sure that your geologic features are understood well enough. This is to make sure, again, you want to have your oxidation contaminants going where they're supposed to, and make sure that it's going to hit every single area of your contamination to make sure none of it is left behind. And this next slide is just kind of an overview on what kinds of contaminants each of these methods are good for. So for soil stabilization, it works really well for metals and inorganics, but it doesn't work as well for VOCs. For permeable reactive barriers, it's really good for VOCs, which is the opposite of soil stabilization, but it's not as good as catching those nitrates and phosphates. These nitrates and phosphates are typically anionic substances, which means that when you're doing your permeable reactive barriers, which typically use chemistry to make sure that they're all working in that way and removing your contamination, it can be difficult to use those anionic substances just in the way that the chemistry is working with your barrier. And for oxidation reduction, it's really good at handling VOCs again, but not as good as handling your inorganics, mainly because your oxidation reduction relies on having that organic compound structure in order to fully remove your contaminants and be able to solve those issues.
So now we are going to get into the field implementation of these remediation methods, starting here with pump and treat. Pump and treat is one of the most common remediation methods used for groundwater remediation. The idea behind it is to extract contaminated groundwater from the subsurface and treat it above ground. And then we can either discharge it, recycle it, or re-inject it back into the aquifer. So the first major component when planning a pump and treat operation is the hydraulic capture. We need to plan to make sure that these wells will overlap each other, the capture zones that they create. This will allow for the most effective removal of the contaminants. Next step in planning is the drilling and the pumping and extraction system being installed. This is where the groundwater will be withdrawn through these wells using pumps, and then it's conveyed with piping to the treatment system at the surface. Another important aspect here is drilling and installing monitoring wells. These will be installed up gradient, within, and down gradient of the plume to confirm that hydraulic capture is being achieved and to track how contaminant concentrations change over time. These wells provide the data needed to verify that the system is actually working as intended and when the system can come to a close. Once extracted, the groundwater will move to the above ground treatment system. Depending on the type of contamination, this may include treatment units like air strippers, granular activated carbon, or other chemical and physical treatment processes. The purpose is to remove the contaminants from the water before it is discharged or reused. The final step, as alluded to before, is recycling or re-injecting of the treated water. In some systems, the water is discharged after meeting regulatory limits, while in others, it will be re-injected into the aquifer to help maintain hydraulic control or support groundwater restoration. So this slide will go over the field implementation of slurry walls. So just a reminder, slurry walls are vertical, low permeability barriers that are used to contain contaminated groundwater and limit plume migration. So this process will typically begin with the execution of trench excavation. Backhoes or long reach excavators are used to dig a narrow trench along the planned wall alignment. And as excavation proceeds, the trench will be kept full of slurry. This slurry is a bentonite water mixture that provides hydrostatic support to the trench walls and prevents them from collapsing in on themselves before the final material is placed. Uh, Before and during operation, the bentonite slurry must be mixed to the proper consistency so it can provide enough support and maintain the trench geometry during and after excavation. Some additional equipment that may be required include slurry mixing tanks, pumps, piping, and other delivery systems to circulate the slurry into the trench. In addition to the slurry providing support during installation, the lower diagram shows steel sections um, that, in addition to the slurry, counteracts the surrounding ground pressure, helping keep the trench open while construction continues. That support is what allows the barrier to be installed safely and continuously before the final low permeability wall is completed. This slide will show the field implementation of sheet piles, which are used as vertical containment barriers to limit groundwater flow and contaminant migration, similar to that of the slurry walls. The first key component here is the interlocking steel sheet piles themselves. Each sheet has shaped edges that lock into the next one, which will allow for the wall to function as a connected unit rather than individual separate elements. Installation is carried out through pile driving, and depending on site conditions, this can be either done with a vibratory hammer or an impact hammer. In the lower image there, you can see a vibratory hammer that is attached to a piling rig. This type of hammer uses vibration to reduce soil resistance and to help drive the sheet piles into the ground. Vibratory hammers are typically more effective in softer or more penetrable soils, while impact hammers are used in harder, more dense, and connected soils. In the top image there, you can see a crawler crane. Crawler cranes and piling rigs are used to lift, align, and position the sheet piles vertically before and during the driving process. This will play these both of these equipments play critical roles in maintaining the proper wall alignment and ensuring that each component of the system is installed correctly for uh, correct system performance. Another important consideration here is ensuring low permeability. While the steel itself is essentially impermeable, the overall wall performance depends on how well the interlocks fit together and whether leakage to the joints can be minimized. In some cases, sealants may be used to improve the overall containment of the system. Finally, sheet piles are commonly installed in conjunction with a natural low permeability layer. Um, how it's typically described is that these piles are driven deep enough to key into a clay layer or another confining unit so that the groundwater cannot easily bypass the wall by flowing underneath it. So now we will move on to discussing field implementation for surface caps. Surface caps are used to isolate contaminated soil or waste from the surrounding environment by placing a layered cover over the site. These are typically seen in landfills, so they're alternatively called landfill caps. Uh, the main purpose of these is to reduce infiltration, limit contaminant leaching, and provide long-term containment of that waste. So the first step of this process is subgrade preparation. Before installation of the cap, the site surface has to be graded and prepared so it provides a stable base. During this process, a proper slope is created. This is important for directing water away from the capped area and not allowing it to pool on the surface. The next part of this process is installing a low permeability layer. This is one of the most important steps of the process because it acts as the main barrier to downward water movement. So you can see in this image here at the bottom right, there's a 2-foot clay liner as well as a thin synthetic membrane liner. These are the main barriers of that downward water movement. There are some additional layers, like a drainage layer. This is used to help move water laterally off the cap that does penetrate to that layer. There is also protective layers and stability layers like the sand and the top layer, which is uh, just basic soil, which vegetation is planted in and it's grown in order to help remove some of that downward water movement and promote evapotranspiration. Vegetation also uh, makes the surrounding area look better, as this area used to be a landfill. Making it greener is provides more of a purpose than just the prevention of water movement. This image here shows an early portion of the installation. You can see that the slope and the subgrade preparation has been done, and the low permeability layer is installed. This is what the synthetic membrane would look like. And then this image here will show a more complete process. You can see that a lot of the vegetation is grown already, and you can still see that slope is maintained, which prevents uh, a large amount of pooling of water above this cap. To construct these caps, significant earth moving and compaction equipment is required. Equipment like bulldozers, excavators, and rollers are used to place soil, shape the surface, and compact the layers so that the design will meet the specifications. Finally, some surface caps do include a gas control system. This is important at sites where gas may be generated beneath the cap. If the gas is not properly managed, pressure can build up and affect the integrity of the cover. So, vents or gas collection of some sort may be included as a part of the design. This slide shows the field implementation of soil solidification and stabilization. This is a remediation method to reduce the overall mobility of contaminants located in soil by mixing the soil with different kinds of binding reagents. So the first part of the process is to mix the soil with those reagents. These typically would include cement, lime, or fly ash. These are added to help bind the soil particles together and reduce the overall permeability. This process can also improve the strength and durability of the treated soil in the area. As shown here on the image to the right, the process requires a full treatment setup. You can see the reagent and water tank that supply the materials needed for uh, s- the solidification and stabilization process. Also in the image, you can see the use of an auger and deep soil mixing equipment. These extend down into the contaminated zone, and the augers rotate through the soil and blend the reagents directly into the subsurface. So this would be an example of an in situ approach. This method can also be done ex situ, where the soil would be excavated first and then mixed above ground using equipment like pug mills or rotary mills. That approach can provide more controlled mixing, but it requires excavators and excavation and additional material handling, so it can be more costly. S- The final step would be quality control of the project. After mixing, the treated soil has to be checked to make sure that the reagents were distributed properly and that the final material has the required strength, permeability, and containment performance desired for the project. This slide will go over the field implementation of permeable reactive barriers, or PRBs. A PRB is an in situ groundwater treatment system that is installed directly across the path of a contaminated plume so that groundwater flows through a reactive treatment zone. The first important technique in the design is placing the barrier across the plume path. PRBs are installed perpendicular to the groundwater flow, as seen in the image here. This is done so that contaminated groundwater is intercepted as it moves through the subsurface. In terms of layout, the system can be either built as a continuous uh, reactive wall or as a funnel and gate design. In a continuous wall, the entire barrier is filled with a reactive media. That is what you see in that image there. In a funnel and gate system, impermeable sections like sheet piles or slurry walls, as we discussed earlier, can be used to direct groundwater towards a smaller reactive gate. After the design is chosen, reactive media will be installed uh, within that design. The media may be installed by excavating a trench and backfilling it. It could be installed by creating a series of overlapping borings or by using injection and fracture placement methods to create a reactive treatment zone within the subsurface. Because of that, PRBs typically require substantial excavation and drilling equipment. Common equipment that may be used include excavators, backhoes, continuous trenchers, and drill rigs. These all depend on the barrier design and depth and the site geology. Also, we need to focus on media delivery. This is needed to bring the reactive material to the installation area and place it accurately. Equipment for this part of the project can include delivery trucks, hoppers, pumps, and mixing or feed systems that place the reactive media into the trench or boreholes. A monitoring well network is another essential part of the setup. Monitoring wells are used up gradient and down gradient, as well as within the barrier, to confirm plume interception, evaluate groundwater flow throughout the system, and to track contaminant breakthrough over time. So this slide is the last slide of the field implementation section, and it will go over in situ oxidation and reduction. In situ oxidation and reduction is a treatment method that treats contamination directly within the subsurface by injecting reactive amendments into the soil or into the groundwater. The first key component here is the use of injection wells or temporary injection points. These are installed so that the oxidant or reductant can be delivered directly into the contaminated zone. Their placement is important because the amendment has to reach the source area or the dissolved plume in order for the treatment to be effective. Another part of the setup is the reagent storage and the reagent mixing system. At the surface, the treated chemical is stored and prepared prior to injection. The equipment necessary for this includes storage tanks, water for dilution if that's necessary, as well as mixing systems that make sure the amendment is delivered at the right concentration. Once prepared, the reagent is moved through pumps and distribution lines. The pumps provide the pressure that's necessary for the movement of the reagent through the pipes, and the piping network will distribute the reagent to the treatment area. Several types of injection equipment can be used depending on site conditions and designs. Direct push rigs are often used for temporary or closely spaced injection points for smaller or shallow uh, contaminated zones. Drill rigs are used when deeper installations or permanent wells are being installed. And in some cases, we can see the use of well-based injection there, where screened wells are installed for repeated amendment delivery over time. During this process, there's a possibility of extraction and recirculation. In the diagrams, you can see on the right, the top one, there is no extraction, recirculation. In the bottom one, you can see that the reagent is injected and then the treated water is piped back out. This kind of setup can be useful when more hydraulic control is necessary or when the goal is to increase contact between the amendment and the contaminant mass. As for this method and most other methods, monitoring wells are essential for operation. Um, the monitoring wells in the diagrams here are used to track amendment distribution, the groundwater chemistry, and the contaminant concentrations over time. These wells help to confirm whether the treatment is reaching the target zone and whether contaminant levels are actually decreasing.
Okay, so now we're moving into demonstration levels, which is where we look at how these methods are actually applied in real world situations. So, containment methods are widely used at Superfund and industrial sites, either as interim solutions or long term controls. These are especially important when contamination is either too widespread or too complex to remove immediately. So, for example, if a contaminant plume has already spread deep into an aquifer, full removal becomes super expensive and very difficult. So, in those cases, containment is used to just stop the spread and reduce the immediate risk to human health and the environment. These systems are almost always paired with monitoring networks as well. So, monitoring wells allow engineers to track plume movement and verify that containment is working over time. Finally, the key takeaway here is that containment doesn't remove contamination, it just controls its movement. So, it essentially buys time until a more permanent solution can be implemented. Our first case study is on pump and treat, which is a form of hydraulic containment. So this focuses on pump and treat at the Savannah River site in South Carolina. The Savannah River site is a large U.S. Department of Energy facility that was used for nuclear weapons material production during the Cold War. So because of that history, the site has a lot of contamination, including chlorinated solvents and radioactive materials in the groundwater. The geology at the site includes layered sediments with varying levels of permeability, which makes the contaminant movement somewhat unpredictable and difficult to fully clean up. So, to manage this, engineers installed extraction wells to create hydraulic capture zones. These wells lower the water table locally, forming what's called a cone of depression, which pulls contaminated groundwater towards the wells. Once extracted, the groundwater is treated above ground using processes like air stripping or carbon absorption, depending on the contaminant, and then either discharged or re-injected back in. This system has been very effective at preventing the plume from spreading into nearby waters like the Savannah River, which is critical for protecting downstream ecosystems and water supplies. However, one major limitation is that contaminants can remain trapped in low permeability areas like where they're full of clay, and so these slowly release contamination over time, which is why systems like this often need to operate for decades. So the key insight here is that pump and treat is reliable for containment and risk reduction, but not always efficient for complete remediation because it's too slow. So our next case study will look at slurry wall containment. Our site here is Love Canal in Niagara Falls, New York, which is one of the most well-known environmental disasters in U.S. history. So originally, Love Canal was used as a disposal site for chemical waste by the Hooker Chemical Company. And so over time, thousands of tons of hazardous waste were buried there, and then eventually the chemicals started leaching into the surrounding neighborhoods. This led, obviously, to serious health concerns for all of the citizens living there, including the groundwater becoming contaminated and vapor intruding into the homes. This then triggered federal action and helped establish the Superfund program. So to contain the contamination, engineers installed a slurry wall around the site. It's constructed by excavating a trench out and filling it with a low permeability mixture, normally soil and bentonite, which prevents groundwater from flowing through. A surface cap was also added to reduce infiltration from rainfall, which helped minimize the leachate building up. Together, these systems significantly reduced the movement of the contaminants away from the site. But however, slurry walls are not perfect barriers. They can obviously have some leakage at certain points and have imperfections while they've been sitting there over time. So that's why long-term monitoring is essential for these, including groundwater sampling and sometimes taking pressure measurements. Finally, the key insight, slurry walls are very effective for isolating contamination, especially when paired with the surface caps, but they require long-term maintenance and oversight. Our final case study for the containment methods is going to look at surface capping on its own. So this case study's site is Fresh Kills Landfill in Staten Island, New York, which was once the largest landfill in the world. It operated for decades and received millions of tons of solid waste, but today it is being redeveloped into one of the largest parks in New York City. So to safely reuse the site, engineers installed a multi-layer cap system over the landfill. This cap included a geomembrane liner, compacted soil layers, drainage layers, and vegetation. Each layer here has a specific function. For example, the geomembrane acts as a barrier to water infiltration, while the drainage layer directs water away from the surface. The main goal is to reduce infiltration of rainwater into the waste. Without a cap, rainwater would just percolate throughout the landfill and create leachate, which can carry contaminants into the groundwater. By minimizing infiltration, the cap reduces this leachate generating and helps stabilize the waste mass. Another important function is gas control. Because landfills produce methane and other dangerous gases, so caps are often integrated with gas collection systems. At Fresh Kills Landfill, this approach has been successful enough to allow redevelopment of the site into a public green space, which is a very major benefit. However, caps do require ongoing maintenance. The vegetation needs to be managed, erosion needs to be controlled, and you need to monitor the integrity of the liner all the time. So, key insight here, this is best for preventing exposure and infiltration, but not for plume cleanup because it doesn't remove contaminants, and it will also rely on long-term maintenance. Now we are moving into ground modification methods. Unlike containment methods, these aim to treat contamination directly in place. So that means the soil or groundwater doesn't get removed. It's altered chemically or physically underground. So these methods are especially useful for source zones where contaminant concentrations are the highest, and also for areas that are difficult to access. Because they directly target contaminants, they can often achieve faster remediation compared to just containment alone. However, they typically require a much better understanding of subsurface conditions like soil properties and groundwater flow. Our first case study here for ground modification methods is going to look at permeable reactive barriers, also known as PRBs. So this case study is at the Elizabeth City Coast Guard site in North Carolina. This was used for aircraft maintenance and repair, which then led to groundwater contamination with hexavalent chromium, which is a very toxic and very mobile form of chromium. So the site is located near bodies of water, so controlling the spread of contamination was very important. To address this challenge, engineers installed a permeable reactive barrier across the path of the contaminant plume. So unlike slurry walls, which we talked about before, PRBs are designed to allow groundwater to flow through them. The barrier is filled with reactive materials, typically zero-valent iron. So as the contaminated groundwater passes through the barrier, chemical reactions will occur. In this case, the hexavalent chromium is reduced to trivalent chromium, which is much less toxic and less mobile. One of the major advantages of PRBs is that they are passive systems, so once they are installed, they don't require continuous pumping or any extra energy input. However, their effectiveness does heavily depend on the groundwater flow direction and the velocity, so if the plume bypasses the barrier, the system then becomes ineffective. Also, over time, the reactive material can become clogged, which reduces the performance of the PRB. Key insight, the PRBs are highly effective and low maintenance. They're very effective for metals and redox-sensitive contaminants, but they require a good understanding of the site hydrogeology and depend heavily on groundwater flow and velocity. Our next ground modification case study is looking at soil stabilization. The site of this case study is the Tar Creek Superfund site in Oklahoma, which is part of a historic mining district. So mining activities there left behind large amounts of waste containing heavy metals like lead and zinc. These contaminants spread into the soil and water, clearly creating serious environmental and health risks. So at this site, soil stabilization was used to reduce the mobility of the contaminants. This involves mixing the contaminated soil with binding agents like cement, lime, or fly ash. These materials chemically react with the contaminants and physically encapsulate them within a solid matrix. This reduces the ability of the contaminants to leach into the groundwater or be transported by surface runoff. Another benefit is that it improves the mechanical strength of the soil, which can help prevent erosion and keep the structure stable. However, this method does not remove contaminants, it just immobilizes them, so that means that long-term stability is critical. It's also less effective for organic contaminants like VOCs, which are not easily bound in the same way as metals are. So key insight here is that soil stabilization is very effective for metals, but it is less effective for VOCs and requires careful design to ensure long-term containment. Our final case study on the ground modification methods is going to look at in situ chemical oxidation. So the site for this case study is Kelly Air Force Base in Texas, which is now a part of a joint base in San Antonio. This site was contaminated with chlorinated solvents from doing maintenance on aircraft like we saw in the Coast Guard example earlier. These contaminants are very dense and can sink below the water table, forming DNAPLs, which we know are very difficult to remediate. So to address this, in situ chemical oxidation was used. This involves injecting strong oxidizing agents such as permanganate directly into the subsurface through wells. These chemicals then react with the contaminants underground and break them down into less harmful compounds, such as carbon dioxide and water. One major advantage of this method is speed. It has rapid contaminant reduction, so compared to pump and treat, it can significantly reduce the concentrations in a much shorter time. However, the effectiveness depends on how well the oxidant is distributed underground. So, for example, if the subsurface is highly heterogeneous, the chemicals may not reach all of the contaminated zones. There's also some potential side effects such as heat generation underground, which makes you need to have a detailed site characterization. Make sure you know what the subsurface is like before going in with the oxidation. So, key insight here, a very fast, rapid method, but it requires good subsurface characterization because of potential side effects that can arise.
Now for applicability and limitations. First, we'll talk about the containment method. As noted before, containment methods are often temporary. This is important to note because this remediation method has a focus on containing, not removing. If a contaminant is in an area where it has a high effect on ecosystem life or is part of a drinking water aquifer, it will likely cause harm. In those cases, it's not the best option to choose. On the other hand, if it has an impact on those ecosystems or drinking water aquifers that are nearby, this is a good option as it can quickly contain the contaminants where they are until a better solution is found, and it will protect that human ecosystem health. So the further away it is from the place, the better the containment method is used for, because then you have that time to pick your better solution. But if it is contaminated right in that area, it's probably not the best choice. This temporary feature also means that it will run for a long time, so continuous monitoring is essential. This ensures that over time, the system is still working to its full capacity. If it's not working, the monitoring allows the operators to make adjustments in a timely manner to make sure that everything is still running smoothly. So now going into more specific methods, we'll talk about the pump and treat system. This system has factors to be considered before you even implement it. And one of those biggest things is that they require a lot of parts to the system that other methods may not have. There's the infrastructure on the ground that needed to remove the contaminants, but you also need the whole piping system and a method of bringing that contaminated water to a treatment facility where it can get cleaned. So you need to have all the pipes that will go there and make sure you have a transportation plan, because sometimes the treatment facilities are right above ground there or they have to be transported somewhere else. And then once that treated water is done, that needs a place to go and be discharged from. So you also need to make sure you have a place for that. And all of those systems need different permitting, so this is a more, timely process if permitting takes a while. But another aspect of pump and treat systems is that they're often used for a long period of time. This means that it needs to be flexible so that changes can be made as time goes on. For slurry walls, one of the main things to consider is that they are likely to degrade over time. There's a lot of testing in laboratories prior to construction to ensure the durability and strength of the wall and how to use correct chemicals in order for it to reach their desired specifications. However, these walls are meant to be in place for a long time, and it is not possible for the materials to avoid degradation forever. So as much as you can try to test it and make things so that it's not going to degrade, it likely will. These things can happen from just pressure buildup, chemical weathering, and seismic activity can all factor into the degradation of the wall. For capping, there's not as much infrastructure needed compared to other methods. This is an advantage for this method, as well as the system has a lower potential for contaminant resuspension. The main component to it is the liner at the bottom prevents toxic leachate from going out. So like when it rains or there's stormwater or other kind of runoff that goes into the system, it's going to go through your contaminated soil, and that liner is going to prevent it from going out. And once you do the liner, you put a cap on top of it. There are multiple different kinds of caps you can do. So you can do synthetic cap cover, but often they're soil caps. So like the one you see in the picture on the right, you can't even tell that that's probably a landfill of some kind, something that has a cap on it. But with this cap, you have to make sure that you're accounting for all of the wildlife in the area, so the plants and animals, because they might want to grow and habitat that area. But however, because you are still on unstable areas, so it's likely filled with a lot of contaminated water and a lot of contaminated soils, you don't want it to puncture or leak out anywhere. So scientists or whoever is building it may design it in a way that they are going to put specific soils or specific vegetation on it that will discourage animals or plants from going onto it. For example, if you want to avoid any burrowing animals from going down into it, because they just may go down too far into contaminated soils and both compromise their health as well as the structure of the cap. Now moving on to ground modification methods. The first one is soil stabilization. This is a method that requires heavy testing before it's implemented as well. It's important to test the mixing speed, the soil treatment rate, and everything else to ensure that everything will go in plan once it is in action. Once you start implementing, it's hard to stop, so it's important that you get it right on the first try. So this testing is really important. Diagrams on the right show different examples of strength testing. You can see where things have failed or where things are good. And this just helps you get a good idea of what kind of chemicals you need to use in order for it to be as efficient as possible. Testing is also important to see if heat will be formed. If there's too much heat from the injections, volatiles can come out, and this causes hazards to both the workers of the construction site as well as just the neighboring areas, as it will spread out into the air that can be harder to control. Soil stabilization is also a method that treats the source area and can be a pretty quick solution, which is pretty appealing for most methods. And the last factor to consider is future use must be considered. So the stabilization in the ground obviously is going to affect the way that you can use that land in the future. So it's important that good documentation is kept of everything so you can make sure that future people know what they can do on this site. For example, there are some landfills that have like stable fill in them, which can be used for like golf courses or soccer fields or things like that. But you also want to be careful on what you put on top in case it does compromise the system that you have built. For permeable reactive barriers, it is important to consider that this process can be slow. What we just talked about, soil stabilization, is a relatively quick solution, but permeable reactive barriers are not. It can be sped up by using an aggressive permeable reactive barrier, but this has give and takes with other things, so it may cause other unwanted consequences. It's also highly important to know what the groundwater flow direction is like. The map on the right is a contour map that shows how groundwater is going to flow. This is really important because you want to know where to place your barrier. If the groundwater flow is not flowing in the direction of your barrier, it's not going to be effective at all, and it's just going to be in place for no reason. So this is an important step. This method also has the capability to remediate an entire plume, so not as much just for the source, but it can be for everywhere that it's going through. But because it is a long-term kind of solution or remediation technique, performance may decrease over time. So again, it's going to have that degradation, and because permeable reactive barriers also have chemical components, those are just going to wear out over time. This can be solved by replacing them every so often, but again, as much testing is done prior to ensure that it's going to be stable and effective for as long as possible. And one final thing to consider are nearby dynamic loadings. So if there's excavations or dewatering that are happening in the nearby area, it's going to impact the direction that the groundwater is going to flow. So again, knowing where your groundwater flow direction is going to be really important for this kind of method, because you want to ensure that your groundwater flow is going through your barrier and it's not either going to go around it, go the opposite direction, or just go somewhere else that's not accounted for. And then the final method is oxidation. So this process is considered really fast, probably the fastest of the three talked about for ground modification, as they are injections that clean up the contaminants directly through chemical reactions. So once they inject it, the chemical reactions are pretty much immediately going to happen. This makes it an appealing option. However, though it sounds like a one and done solution, you still have to have your continuous monitoring, make sure that everything is still set in place and that the contaminants are still going away as predicted. And like the permeable reactive barrier, it's important that you understand groundwater flow, as typically multiple injection sites are needed. Their radius of influence, which is just the area that the chemicals can spread from the injection wells, is not that large. So you want to make sure that you're covering all the contaminant areas as possible. So you need to make sure that your groundwater flow is going through the right places. So similar like the pump and treat where they have those like cones of depression, kind of similar thing where you want to make sure you're getting all the groundwater flow and getting all of your contaminated water all fixed up in the right place. A method of oxidation is groundwater recirculation, which is what this image on the right shows. So there's parts where things are injected and places where things are taken out. So you kind of get that recirculating effect with clean water going in and contaminated water going out to make that cycle and to allow the oxidation process to really go through as many cycles as possible to clean it up as best as it can. Oxidation also is a good method to remove an entire plume, but it also is one of those methods that requires permitting.
Now we're going to shift into costs. So we'll start with the containment methods here, the 4 different containment methods. One important thing to understand is that remediation costs are highly site specific, but these we can still look at typical ranges and what drives those costs normally. So starting with the pump and treat, the unit cost is roughly $100 to $250 per cubic meter treated. At first glance, that might seem reasonable. The capital cost for installation, things like wells, piping, treatment systems, can range from about $50,000 to several $100,000 depending on the size of the system. But the real cost driver here is operation and maintenance. So these systems often cost hundreds of thousands of dollars per year to operate, and they may need to run for decades. So the upfront cost being moderate to reasonable is a little skewed because the total life cycle cost can be extremely high. And the reason for that comes down to hydrogeology. Because groundwater moves slowly and contaminants can become trapped in the low permeability zones. So even after years of pumping, you may still see residual contamination like slowly diffusing out, which keeps the system running. So moving on to the slurry walls, these are typically priced per square meter of wall installed, which is around $100 to $400 per square meter. The cost depends heavily on depth, the soil conditions, and the type of slurry used. So soil versus cement bentonite, for example. Another example, deeper walls require more excavation and more material, which will increase the cost, obviously. If the soil is unstable, additional support systems may be needed during construction as well. So while slurry walls can be relatively cost effective for containment, they are very sensitive to site conditions. The sheet piles are generally more expensive, around $200 to $600 per square meter. That's largely because they use steel and require heavy equipment like impact hammers for installation. They do provide strong structural support, which can be important in certain applications, but they also come with additional costs, such as sealing joints to prevent leakage and corrosion protection over time. Finally, with the surface caps, they are typically one of the lowest cost containment options, especially when you're applying them over large areas. So the costs here range from about $50,000 to $500,000 per acre. These costs include the multiple layers, geomembranes, drainage systems, vegetation, all that. While the installation cost is relatively low compared to the other methods, the caps still require long-term maintenance when you're monitoring for erosion and the integrity of the liner holding up over time. So overall, the big takeaway for the containment methods is they often have lower upfront costs, but they result in long-term expenses because of operation and monitoring over years to decades. Now onto the ground modification methods, the costs of these 3 technologies. These tend to have a different cost structure compared to the containment methods. So starting with soil stabilization or solidification, the costs are typically higher on a per volume basis. So from $4,300 to $6,500 per cubic meter in some cases, which seems very expensive, but it's important to understand what you're getting for that cost. So this method involves mixing contaminated soil with reagents like cement or lime, which chemically bind the contaminants and like physically encapsulate them. So it provides a more permanent solution. Once the contaminants are immobilized, there's like very little need for long-term operation or maintenance costs, which offset the higher upfront cost for this technology. Next are the permeable reactive barriers, or PRBs. These typically cost around $200 to $1,000 per square meter installed. The wide range comes from factors like the type of reactive material used and the method of installation. For example, zero valent iron is commonly used but can be an expensive method, especially for large systems. Installation can also vary because you can use trenching or injection methods, which also affects the cost. So there's a little bit of a range there. The advantage of PRBs is that they are passive systems. So like the stabilization, once installed, the operation and maintenance costs are going to be relatively low. However, over time, this material specifically can become clogged or depleted, so it may require some replacement costs, but relatively low O&M costs here. And then finally, we have the in situ chemical oxidation method. So the costs here are typically in the range of $100 to $300 per cubic meter treated. The main cost components here are the chemicals themselves, and the injection system, so the equipment involved as well. The amount of chemical required depends on the contaminant concentration and the soil's natural oxidant demand, which can significantly affect the cost too. The in situ chemical oxidation can be very effective and relatively fast compared to the other methods, but it requires careful design to ensure that the oxidant reaches all the contaminated zones. So cost will vary with the design methods as well. The key takeaway for all of these ground modification methods is that they generally have higher upfront costs, but they achieve faster remediation and also will have less operation and maintenance costs long term. So these long term costs will even out at the end of the day. Okay, finally, we'll talk about availability, which is a really important factor when deciding which remediation method to use in practice. Starting with the first bullet point here, these technologies are widely available through major organizations like the EPA, the Federal Remediation Technologies Roundtable, and the Interstate Technology and Regulatory Council. So the EPA plays a major role by providing regulatory oversight, guidance documents, case studies, stuff like that through programs like Superfund. These resources then help engineers understand what methods have been successful at similar sites. The FRTR is particularly useful because it maintains a database of proven remediation technologies, including the cost and performance data from real-life projects. So this helps engineers compare options and make informed decisions on what technology to choose. The ITRC focuses more on technical guidance and best practices. They kind of provide detailed documents on how to design and implement methods like in situ oxidation or soil stabilization. So overall, these organizations make the technologies not only available, but also well documented and supported and very helpful with decision-making processes. So next, the maturity of the technologies. So pump and treat systems are the most established and widely used. They've been implemented for decades and their behavior is very well understood now at this point. And so because of this, they are often considered a reliable, low-risk option. Similarly, slurry walls and surface caps are based on standard geotechnical construction practices. They are also very widely used in civil engineering, so there's a large pool of contractors and experience available with these. On the other hand, the PRBs and in situ chemical oxidation are more specialized technologies. While they are becoming more common, they still require more expertise in things such as the subsurface chemistry and hydrogeology. So this difference in maturity affects not only the availability, but also the perceived risk of using certain technologies. So on to contractor availability. Different remediation methods will require different types of contractors. So for example, civil or geotechnical contractors typically handle technologies like the slurry walls, sheet piles, and caps because they are very construction-heavy methods that rely on excavation and earth-moving equipment. Environmental remediation firms, on the other hand, specialize in systems like pump and treat or chemical injection because these require knowledge of groundwater flow, contaminant behavior, and certain treatment processes regarding chemicals. Then there are specialized vendors, particularly for technologies like the PRBs or deep soil mixing. These companies often have the right equipment or materials that may not be available for certain people or not available in all regions. So even if a technology is technically feasible, it might not be practical if the right contractors aren't available nearby or ready for hire. Now, looking at the site accessibility considerations, urban sites generally have better access to infrastructure, equipment, utilities. So this makes it easier to install and operate remediation systems, just because of the easier access to everything. For example, you may have access to power for pumps, a lot of space for treatment systems, and established roads to be able to transport equipment easily. In contrast, remote sites can be much more challenging. Equipment has to be transported over long distances, which will increase the mobilization costs. And there may also be limited access to labor or specialized contractors due to it being so far away. Another important factor is depth. If contamination is deep underground, it's going to require specialized drilling or injection rigs. And so this is going to add complexity to everything and up the cost, obviously, and can also limit which methods can be used. Finally, with the permitting and regulatory factors, many remediation methods require permits before they can be implemented or used. For example, pump and treat often requires permits for groundwater extraction and then discharging the treated water. So these permits ensure that the system doesn't negatively impact any surrounding bodies of water or water resources. For chemical injection methods like the in situ oxidation or reduction, additional approvals may be needed because of certain chemicals that are being introduced into the ground. Regulators want to ensure that these chemicals aren't going to create any unintended consequences or hurt other things that were not foreseen. The permitting process can take time. Sometimes it takes months or even years and can delay project implementation. So that does have to be kept in mind. But regulatory approval doesn't just affect whether the method can be used, it also will affect the timeline and just overall feasibility of the project.